Another very powerful oxidizing agent is potassium permanganate, KMnO4. So let us go over oxidation of aldehydes using aqueous solution of Mn7. Manganese is in 7 oxidation state here. So this you can oxidation of aldehydes. To carboxylic acids. Using aqueous solutions of Mn7. So this you can do it in neutral or acidic or alkaline medium. So let us go over oxidation in acidic medium using KMnO4. So the aldehyde can be hydrolyzed to hydrates, that is geminal diols. So in acidic medium, this is going to pick up proton. And this is going to attack the carbon. Water is going to leave. So what we have now is manganate ester. So this is going to attack the proton. The bond falls back on oxygen. So this pair of electrons fall back on electron deficient manganese to give you carboxylic acid. Plus so while you have oxidized aldehyde to carboxylic acid, meanwhile you have reduced manganese from its +7 oxidation state to +5 oxidation state. You could also oxidize primary alcohols with in KMnO4 in alkaline medium. So potassium permanganate is a very powerful oxidant, and it is going to oxidize even benzylic methyl group. So this is a benzylic methyl group. So KMnO4 is such a powerful oxidizing agent. Even this group can be oxidized to carboxylic acid. So it's not just chromium 6 oxidizing agents or potassium permanganate that's going to oxidize aldehydes. Aldehydes could also be oxidized to carboxylic acids. Using some very common oxidizing agents like nitric acid, potassium dichromate, so even mild oxidizing agents like Tollens reagent and Fehling's reagent also oxidize aldehydes to carboxylic acids. Now let us go over so now we have seen the preparation of carboxylic acids from oxidation of alcohols and aldehydes. So now let us go through the preparation of carboxylic acids using Grignard reagents. Carboxylic acids using Grignard reagents. Grignard reagents like RMGX, react with carbon dioxide. Carbon dioxide is an excellent electrophile. So goes in dry ether to give you a carboxylic salt, carboxylate salt. And protonating this salt with acid gives you carboxylic acid with one carbon more than what you started here. So you have basically ascended the series than the starting organometallic. So from alkyl halides to acetic acid, there are going to be 3 steps. It just involves 3 steps. First is the formation of organometallic. So suppose we have alkyl bromide, reacts with magnesium, dry ether. So it's going to form Grignard reagent RMgBr. The formation of Grignard reagent via oxidative insertion of magnesium into alkyl halides. So this is our first step. The second step is reaction of organometallics with CO2. GX. This will give you carboxylate salt. The third step is acidic workup or quenching. Acidic workup or quenching. So it's a good practice to not directly attack but show it this way to get carboxylic acid. So let us go over some specific examples. Consider this example. First step is the formation of Grignard reagent using magnesium in dry ether. So step 1, formation of organometallic. The second step is reaction with the electrophile. So our electrophile here is carbon dioxide. To give you carboxylate salt. The final step is your acidic quenching. Or acidic workup. So you have prepared carboxylic acid from alkyl halides from Grignard reagents. So you are going to get 86% yield here. This is a very good method. Even hindered chlorides, for example, take this. Even hindered chlorides can give you carboxylic acids. So this is going to react with the electrophile, that is carbon dioxide, again in dry ether. And the third step is quenching, acidic workup. So this will give you going to give you 70% yield here. This is very good example. Even the hindered chlorides, okay, can form carboxylic acids. The third preparation method is hydrolysis of nitriles to form carboxylic acids. Carboxylic acids. So take this example. This is a nitrile. Sulfuric acid, 100 degrees Celsius, and 3 hours will give you primary amide. You can hydrolyze amides to carboxylic acids. So let us quickly go over the mechanism here. So this group is also called benzyl group. So this is called benzyl. So I'm just going to use BN. Sometimes benzyl is also represented by BN. So let us go over the mechanism here. So this is going to pick up the proton. The lone pair on nitrogen is going to pick up the proton. Water is going to attack here. Falls back. So this bond is going to fall back on oxygen to give you imine. The lone pair on nitrogen is going to stack the proton, is going to attack the proton and give you iminium ion. This bond falls back and you're going to get our primary amide. So from nitrile, you have got primary amide. Further, amides can be hydrolyzed to carboxylic acid using acidic as well as basic medium. So we'll quickly go over the mechanism. So amides can be hydrolyzed to carboxylic acids under both acidic or basic conditions. So let us go over amide hydrolysis first in acidic condition. We'll take the same So here the lone pair on oxygen is going to pick up the proton. Water is going to attack the carbon. This bond is going to fall back. So this bond fall back. Now next, the lone pair on the nitrogen is going to pick up the proton. So this bond ammonia leaves, and what you have done is you have generated, sorry, it's going to be benzyl group, not the phenyl group, it's going to be benzyl group. So you generated carboxylic acid, and the ammonia that you that has left will pick up proton and form ammonium ion. So this ammonia is protonated again, therefore it completely becomes non-nucleophilic. That is, protonation of this ammonia prevents reverse reaction. So the conditions here are very rigorous. It should be hydrolyzed for 3 hours at 100 degrees Celsius with 70% sulfuric acid. These are very rigorous conditions, and you will end up with 70% of yield. You would end up with 70% of acid. So let us now go through hydrolysis of amides in basic medium. Amide hydrolysis. Basic medium. So we'll take the same reactant. This is our primary amide. The hydroxyl groups in basic, the OH minus groups are sufficiently powerful nucleophiles, and they are going to attack the carbon here. They are going to attack the carbon of the amide carbonyl group. So that will So most of the time the hydroxide group, that is this group, is lost again, giving us back the starting materials which we do not want. So nonetheless, at very high temperature, amides are slowly hydrolyzed by concentrated base. That is, this is going to fall back and NH2 minus leaves. So the base here is going to take up the proton, formation of carboxylate anion to form the carboxylate anion. And this is irreversible formation of carboxylate anion. So carboxylate anion is resonance stabilized. Okay. And this formation of carboxylate anion is what drives the reaction forward. So in today's class, we went over the nomenclature of carboxylic acids. We went over the preparation of carboxylic acids. First, by oxidation of alcohols and aldehydes. Next, we went over preparation of carboxylic acids using Grignard reagents. Here in your syllabus, Grignard reagent is given. So it's basically organometallic. You could also use lithium, alkyl lithiums, to generate a carboxylic acid. 3, you have used from nitriles. The last two methods are significant because you have stepped up from the starting material. From the starting material, for example, here if you had started with alkyl halide, you're going to get a carboxylic acid that has one more carbon. So you have basically ascended the series. In both of these, you have got a carboxylic acid with one more carbon atom than the starting material, and that is very significant. In the next class, we'll go through the physical properties and we'll study the acidity of carboxylic acids, and we'll go over a few reactions. Thank you.